Welcome back, grade 10s, to the fourth lesson of motion in one dimension. Now, in the last lesson, we considered scenario 1 and scenario 2. Scenario 1 was looking at position time, velocity time, and acceleration time graphs for a stationary object or an object that is not moving. In scenario 2, we looked at position time, velocity time, and acceleration time graphs for an object moving at a constant velocity. And now in scenario 3, we are looking at constant acceleration. So we will consider the position time, velocity time, and acceleration time graphs of objects moving at a constant acceleration. Now recall that acceleration is defined as the rate of change in velocity. And a constant acceleration means that the velocity changes at a constant rate. So that means that the object speeds up by the same amount every second or slows down by the same amount every second. Let's look at the scenario. Tammy's mom picks her up from school and Tammy gets in the car. And this is our point of origin. Now the car is accelerating, speeding up in the positive direction, which is defined as the direction of the motion. So after 1 second, the car has covered a distance of 5 meters from the origin. After 2 seconds, the car has covered a distance of 15 meters from the origin. After 3 seconds, 30 meters, and after 4 seconds, 50 meters. Now, note that this is not a constant velocity because a constant velocity means that the position or the displacement changes by the same amount every second, whereas here we can see that there is an increase in the change in position every second. So that's obviously then not constant velocity, but rather acceleration. Now also keep in mind that all the way to matric, you're only going to be faced with questions of constant acceleration. So if there is an acceleration, it has to be constant. So we can graph the position time graph of this motion based on the information above, which I've tabulated here, time versus position. Another thing to note is that when you're given a table, the column on the left will always represent the independent variable. And that's a neat tip for biology or science or maths, where you have to graph something and you're not sure which is the independent variable and which is the dependent variable. The x-axis represents the independent variable, and a table will always show the independent variable on the left. The x versus t graph for this motion has a curved shape. This happens to be a parabolic graph. And here we have graphed 5 meters after 1 second, 15 after 2 seconds, 30 after 3 seconds, and 50 after 4 seconds. So an x versus t graph will be curved when the acceleration is constant. When the acceleration is constant, it means that the velocity is not constant, but the velocity is changing by a constant amount. So there's a constant change in velocity every second. We therefore need to calculate the instantaneous velocity at each second in order to be able to graph the velocity time graph. Because we have the values of position and the values of time, we're able to work out the velocity at 1, 2, 3, and 4 seconds so that we're then able to graph the velocity time graph. So the velocity after 1 second is delta x over delta t, which is xf minus xi over tf minus ti. Now we can see that after 1 second, the final position is 5 meters, whereas the initial position was 0 meters, and the final time is 1 second, whereas the initial time was 0 seconds. And so we get a velocity of 5 meters per second. We got a positive answer as expected, which means that the car is traveling in the positive direction, which is the direction of the motion. Now you may calculate the velocity of the car at 2 seconds, 3 seconds, and 4 seconds. And I'd like you to try that on your own. So pause the video, do the calculation, and then unpause. Let's take a look at the velocity after 2 seconds. Delta x over delta t. We always have to show the step. So here we're going to say 15 minus 5, because after 2 seconds the position was 15 meters, and after 1 second the position was 5 meters, over 2 minus 1, because we're looking at that time interval between 1 and 2 seconds. And so we get an answer of 10 meters per second in the direction of the motion. So we can see that the car sped up. It went from 5 meters per second after 1 second to 10 meters per second after 2 seconds. Let's see what happens in the third second. Same calculation, but in this case, we're going to say 30 minus 15 over 3 minus 2. And we can see that the car is speeding up even more. It is now traveling at 15 meters per second in the direction of the motion. And lastly, at 4 seconds, we can calculate the velocity as 50 minus 30 over 4 minus 3, and we get 20 meters per second in the direction of the motion. Now, the velocity time graph is going to be a straight line graph with a single gradient. The reason for that is that the velocity is increasing by the same amount every second, which is indicative of a constant acceleration. And we're going to come to this shortly, but remember that the gradient of a velocity time graph represents acceleration. And here we've got a single gradient, meaning that we have one constant acceleration. So let's take a look here. After 1 second, the car was traveling at a velocity of 5 meters per second. After 2 seconds, 10 meters per second. After 3 seconds, 15 meters per second. And after 4 seconds, 20 meters per second. Now, as I already mentioned, we may calculate the acceleration of the motion based on the gradient of the velocity time graph. And from there, we may graph the acceleration time graph over the 4-second time interval. So now let's take a look at this calculation. Acceleration is change in velocity over change in time, which is Vf minus Vi over Tf minus Ti. Now you may create a right angle triangle wherever you want to on this graph and then read off the respective velocity and time values. But I like to use the entire graph as my right angle triangle. So my final velocity was 20 meters per second. My initial velocity was 0. My final time was 4 seconds, and my initial time was 0 seconds. So that gives us an answer of 5 meters per second squared. Now note that we got a positive answer. A positive acceleration answer means one of two things. It either means slowing down in the negative direction. In this case, clearly the car was speeding up in the direction of the motion. So a plus and a plus makes a plus. The fact that the velocity time graph has a single gradient means that the car's acceleration is constant. The acceleration is not changing. The fact that the velocity time graph has a positive gradient means that the car is traveling in the positive direction. So again, a positive answer might mean speeding up in the positive direction or slowing down in the negative direction. In this scenario, we could see from the data that the car is speeding up, and we also understand from the scenario that the car is moving in the direction of the motion. So now we have calculated that the car travels for 4 seconds at a constant positive acceleration of 5 meters per second squared. And this allows us to graph the acceleration time graph. And so after 1 second, the car was traveling at an acceleration of 5 meters per second squared. After 2 seconds, 5 meters per second squared. Same as after 3 seconds and after 4 seconds. So we end up with a straight line graph that has no gradient. Now recall that the area under an acceleration time graph represents velocity. That's because acceleration is velocity divided by time. And if we rearrange this formula, we can say that velocity is acceleration times time. Now the formula for a square or a rectangle is length times breadth. And if we look at this graph over here, we'll notice that the length is represented by time and the breadth is represented by acceleration. And so if we multiply the two together, we would get the change in velocity. So let's calculate the car's velocity after 1 second based on the acceleration time graph. So after 1 second, the velocity is the acceleration after 1 second times the time after 1 second. The acceleration is 5 meters per second squared times 1 second, and that gives us an acceleration of 5 meters per second in the direction of the motion. Now, if we go back to our earlier calculations, we will see that after 1 second, we did in fact calculate that the velocity was 5 meters per second. So it all has to work out. Now, after 2 seconds, if you had to do the same calculation, you'll find that the velocity is 10 meters per second. And after 3 seconds, you'll find that it's 15 meters per second. We don't expect the velocity to be constant because we're dealing with a graph of constant acceleration. So the car is increasing its velocity every second. So if we wanted to calculate the car's velocity after 4 seconds, then we need to consider this 4-second time interval. So the velocity after 4 seconds is acceleration times time, which is 5 times 4, which is 20 meters per second in the direction of the motion. And again, that is in line with our previous velocity calculations based on position and time. The last thing that we need to consider for scenario 3 is using a tangent in order to work out the instantaneous velocity from a position versus time graph. Now, when we dealt with scenario 2, where the velocity is constant, we have an xt graph that has a single gradient. And that single gradient we use as a right angle triangle to allow us to calculate the velocity throughout the motion. And that velocity is obviously constant. However, in scenario 3, the velocity is not constant. The acceleration is constant. And remember that when the acceleration is constant, then we end up with an x versus t graph that is parabolic. If we want to work out the instantaneous velocity, when it comes to a curved graph like this one, then we need to use a tangent. Now, we already worked out the velocity of the car after 1 second, 2 seconds, 3 seconds, and 4 seconds, but that's because we had values presented to us so that we knew the change in position and the time interval. So using delta x over delta t, we could work out velocity. But you'll see now that a tangent is used to calculate the instantaneous velocity at points on the graph where we don't have values that were given to us. So, for example, after 0.5 seconds or after 3.5 seconds. A tangent is a line that touches the curve only at one point. So in this case, this tangent touches the curve only at this point over here, which is 1.5 seconds into the motion. And this tangent will allow us to work out the instantaneous velocity at 1.5 seconds exactly. So just like in the case of a single gradient graph, we turn the tangent into a right angle triangle because it has a single gradient. I like to extend it all the way to the ends of my graph. I find it easier to then read off my XF and XI values and my TF and TI values. But you can extend your tangent as far as you'd like and make a right angle triangle and read off the two respective X values and the two respective T values. So if we consider scenario 3, we calculated the velocity of the car at 1, 2, 3, and 4 seconds because we had the exact positions of the car at those time intervals. But now let's calculate the gradient of the x versus t graph at 1.5 seconds. We need to find this 1.5 second point, and then we need to draw a tangent. So the tangent again is a straight line that touches the curve at that point but doesn't cross the curve. And at this point over here, at exactly 1.5 seconds, is where the tangent needs to be able to just touch the curve on either side of this dot. This line then represents the slope of the curve at that exact point where it touches, and that would indicate the instantaneous velocity at exactly 1.5 seconds. Like I already mentioned, we may extend this line as far as we like. I find it easier to extend it all the way to the ends of my graph. But from there, we need to read the values of the graph very, very carefully and with great accuracy in order to be able to calculate an accurate velocity for that point in time. So at 1.5 seconds, the velocity can be measured as delta x over delta t, which is xf minus xi over tf minus ti. Now, with careful reading of the graph, I worked out that this value over here is 34. And because I extended my tangent all the way to the bottom, then my initial position is 0. Now, my final time interval, because I extended my tangent all the way to the end of this graph, is 4 seconds, and my initial time for this tangent is 0.5 seconds. And so that gives me an answer of 9.71 meters per second in the direction of the motion. Tangents are quite tricky. Using a tangent, let's calculate the velocity of the car at 3.5 seconds. So here's a 3.5 second mark. Here's my tangent, and I am going to use the entire right angle triangle of this graph over here to calculate the gradient of this tangent, which will give me the instantaneous velocity of the car at 3.5 seconds. So it's xf minus xi over tf minus ti. Reading off this value, I get 49 minus 0 divided by 4 minus 1.5. And that gives me a velocity of 19.6 meters per second in the direction of the motion. That brings us to the end of scenario 3. So now we've covered our 3 motion scenarios. Let's do a summary of each one. When you describe the motion represented by a graph, you should always include whether the object is at rest, moving at a constant velocity, or moving at a constant acceleration. Remember, scenario 1, scenario 2, scenario 3. You also have to mention if the object's moving in the positive or in the negative direction. For acceleration, you must state over and above if the object is speeding up or slowing down. And you should always mention the time interval, the duration of the motion. Let's now look at the relationship between graphs of position, velocity, and acceleration versus time for each scenario, starting with scenario 1 for a stationary object. When an object is stationary, it means that it is not moving, so its position does not change, as we can see on the x versus t graph. And so that means that there is no velocity and there is no acceleration. Scenario 2 is uniform motion. When the motion is uniform, we mean that the object is moving at a constant velocity. Its position, therefore, changes by the same amount every second. So we have a single gradient, straight line, x versus t graph, which represents that the position changes by the same amount at every time interval. Now, if we had to calculate the gradient of the x versus t graph, we would get the value for velocity. Now, the velocity is not changing. Scenario 2 deals with constant velocity, so the v versus t graph is a straight line with zero gradient. Recall that the area under the velocity time graph will represent the total change in position of the object. So, how many meters has the object covered? Because the object's moving at a constant velocity, we have zero gradient here, which therefore translates to zero acceleration. So the object's not speeding up or slowing down. It is moving at a constant speed. Scenario 3 is constant acceleration. When an object's moving at a constant acceleration, it means that the object is moving with a constant change in velocity. Now, that constant change in velocity might be a constant increase in velocity or a constant decrease in velocity. So this is one type of xt graph for constant acceleration, and we're about to go through all 4. Now, in this graph, we can see that the position is changing every second by an increasing amount. We can see that based on this parabolic shape, that the object is speeding up. And also we can see based on this VT straight line graph with a single gradient that the object is speeding up, resulting in a constant acceleration. The object's velocity changes by the same amount every second, resulting in a single gradient velocity time graph. The gradient of the velocity time graph provides us with the acceleration value. So working out this gradient will allow us to work out the value of acceleration, so we may then graph the acceleration time graph for that motion. Recall that the area under the velocity time graph represents the change in position, the delta x of the object. Remember that in this case, because we have a triangle, we don't calculate the area as length times breadth, but rather as half length times breadth. Because the acceleration is not changing, the a versus t graph is a straight line with no gradient. And recall as well that the area under the acceleration time graph will represent the change in velocity of the object. Now, this example indicates 1 out of 4 types of position time graphs for constant acceleration. So let's go through all 4, starting with this one that we've already covered. This shape over here represents a speeding up in the positive direction. And remember that a plus and a plus makes a plus. So this actually represents a positive acceleration. So in this case, the object is speeding up in the positive direction. Now we know that the direction is positive because it is a curve with an upward slope. We also know that the object is speeding up because the graph starts off less steep and then it becomes more steep. What I mean by that is if you had to make a little tangent here, and you had to make a little tangent here, this one over here is a lot steeper than this one over here. This one here has a much sharper angle than this one here. So that tells us that the object starts off more slowly and then the object speeds up. Let's take a look at speeding up in the negative direction. Now, a plus and a minus makes a minus, so we would end up with a negative acceleration. So in this case, the object is slowing down in the positive direction. We know that the direction is positive because we have an upward slope. We know that the object is slowing down. Again, take a look here. We're going from a more steep curve, which means faster, to a less steep curve, which means slower. So that tells us that the object is slowing down. Now, because this is a negative acceleration, your acceleration time graph is negative, meaning that it will be drawn in the 4th quadrant. When you calculate acceleration, you'd get a negative value. And the negative value, that straight line, needs to be drawn in the 4th quadrant. Let's take a look at slowing down in the negative direction. Now remember that a minus and a minus makes a plus. In this case, the object is slowing down in the negative direction. So we know that the direction is negative because we have a downward slope that indicates the direction. Now, how do we know that this object is slowing down? Well, again, you've got to look at the steepness of the slope. So it is going from more steep to less steep. So it is slowing down. This is a positive acceleration, so your acceleration time graph will be positive. You'll get a positive acceleration, so that straight line will be drawn in the 1st quadrant. And finally, speeding up in the negative direction, a plus and a minus makes a minus. So here the object is speeding up in the negative direction. We know that the direction is negative because the curve has a downward slope. And we know that the object's speeding up because we are going from a less steep curve to a more steep curve. So that means that it is speeding up. Because we have a negative acceleration, then we would get a value for acceleration that's negative. So it is going to be drawn in the 4th quadrant. That brings us to the end of the summary on motion graphs. In the next lesson, we will go through some examples and apply everything that we've learned in this section.